In this video, we're going to see how to find the derivatives of power functions and square root functions. And we're also going to see a rule for a constant multiple of a function, find the derivative of that. So first off, the derivative of the power function, derivative of x to the n, is n x to the n minus 1. Now, before I do a little proof of that, just know that this means you take the exponent to the front as a coefficient and decrease the power by 1. Now, if you don't care about a proof, you'll see in the description a link down to the first example. You can skip straight there. But I'm going to give a quick proof of this because you should understand why things are true. So here's a proof. So we start off with the derivative with respect to x of x to the n. And we know that the derivative is going to be the limit as h approaches 0 of x plus h to the n minus x to the n all over h, the limit of the difference quotient. If I expand this out, I will have x to the n as my first term plus n x to the n minus 1 h as my second term. And if you think that through, like when I get squared, I'm going to have x plus h squared. So x squared plus 2xh. If I had x plus h cubed, I'd have x cubed plus 3x squared h. I could get to this idea from either the Pascal's triangle, I can see the pattern, or the binomial theorem. And I'm going to put what I saw one of the professors at MIT do on his online course here. He just said plus junk. And I'll get back to why that's junk shortly. And I have minus x to the n all over h, and I have this limit still going on here. Limit as h approaches 0. Okay, now here's what happens. The x to the n's cancel, and everything in this junk has an h squared or a higher power of h. So when I go and cancel out one of the h's in here, this stuff will all still have h in it. And so this limit will now just equal n x to the n minus 1 because this term goes to 0 as h goes to 0. And that's a quick little proof of that. Now, I didn't specify this, but this only works where we either have binomial theorem or we have Pascal's triangle, which means we're only dealing with natural numbers or whole numbers of n. We're not dealing with negative n's here. We're not dealing with decimal values for n here. I'm going to use this rule for some of those right now, but I'd have to be looking at the derivative of e to the x. That's a nice, easy way to prove this for any n. All right, let's see some examples. So here's the idea. If I have the derivative with respect to x of x to the fourth, I take the 4 to the front, and I have x to the 4 minus 1 is 3 now. Same thing for x to the 7th. I take the 7 to the front, and I decrease the power by 1, so I get 6. Now this one, you might say, well, hold on. This one isn't the same as that, but here's the idea. I can rewrite this as the derivative with respect to x of x to the negative fifth, and now I can use the same rule. I didn't prove it for this. I might include a proof in a later video. I'll definitely do it in class. But it does work this way. So I would take the negative 5 to the front, and I would decrease the power by 1. Keep in mind, negative 5 minus 1 is negative 6. And I don't like the negative exponent, so I will send the x to the negative 6th down to the denominator and get negative 5 over x to the 6th. All right. Next one. The derivative with respect to x of the square root of x is 1 over 2 root x. Now, there are two ways to prove this. The first one just deals with the function itself. So I'd say, okay, we'll consider the derivative with respect to x of the square root of x, and that's going to be the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. Before I get too far into this, again, if you want to skip the proof, you can go down to either the alternate proof, which is the next thing we're going to see, or the example 2, which is an example that includes the square root. And so in here, actually get rid of that for a second. The problem with this is if I put 0 in for h, I get 0 divided by 0 because I have this h down in the denominator. And the way I'm going to fix this is by doing something that seems a little counterproductive. We're going to multiply the top and the bottom by the conjugate, root x plus h plus root x, and root x plus h plus root x down there. Now, usually we've seen to do this to get rid of square roots in the denominator. But what actually happens here is the following. It's actually really nice. The limit as h approaches 0, the square root of x plus h times the square root of x plus h is x plus h. Root x plus h times root x and negative root x times x plus h cancel out. And then negative root x times root x is minus x. In the denominator, I'm not even going to distribute the h here because I'm going to want to get rid of it shortly anyway. So I'll have a root x plus h plus a root x. All right, we can see the x's cancel, and then h divided by h gives me a 1 up there. So now I'm sitting at the limit as h approaches 0 of 1 over root x plus h plus root x. And as h approaches 0, this term here approaches root x, which means this will be 1 over root x plus root x, or 1 over 2 root x. And so we have it proven, as was to be shown. There's an alternate way to prove this that's a little bit quicker, a little bit nicer. It does make the assumption that we haven't quite dealt with yet, but I can look at it this way. The derivative with respect to x of the square root of x, well, the square root of x is x to the 1/2, so this is the derivative with respect to x of x to the 1/2 power. And again, if I make that assumption that this works all the time, I'll prove it eventually. I'll try to remember to put that actually in the note in the video down the road. But I follow the rule. Bring the 1/2 to the front, and then subtract 1 from this exponent. So 1/2 minus 1 is negative 1/2. And the negative exponent brings that x to the denominator. So I have 1 over 2 x to the 1/2. And x to the 1/2 is just the square root of x. And so if we use the power rule, we get this much easier. I don't need to worry about that strange using the conjugate to almost cancel out roots in the numerator. So one more rule in here before I get into some of this. If I have a constant times a function, the constant just comes straight down. I don't need to do anything weird about that constant. So let me put over here. So you just multiply that same constant by the derivative. Now, if you don't want to see a proof, skip on down to the second example, but I will give a quick proof of this. Again, it's worth understanding why things are true. So the derivative with respect to x of c times f of x will be the limit as h approaches 0 of c times f of x plus h minus c times f of x all over h. But I can factor out this c from the numerator and factor it actually all the way out of the limit. There's no h's in this c, so that's going to equal c times the limit as h approaches 0 of f of x plus h minus f of x all over h. And we see right here, this is the limit of the difference quotient. That's just going to be f prime of x. So c times f prime of x. So let's see an example of this. Given f of x is equal to 6 root x, find the equations of the lines tangent and normal to y equals f of x at x equals 4. So we've seen this in previous videos. In order to find these equations, I need the point. To find the point, I just substitute in the x value into the original function. So I find f of 4, which is going to be 6 root 4. The square root of 4 is 2. 6 times 2 is 12. So that means that my point is 412. And I also am going to need the slope. To find the slope, I'm going to use the derivative. So f prime of x, I have a constant 6 times root x. So the derivative is going to be 6 times the derivative of root x, times 1 over 2 root x. And when I multiply an integer by a fraction, it goes to the numerator, so 6 over 2 root x. I can cancel out 6 over 2 and get 3 divided by root x, so that's f prime of x. I want to find this slope at 4, so I'll do f prime of 4 to get the value of the slope, which is going to be 3 over root 4, which is 3/2. And now I have everything I need to actually write these equations. So the tangent equation is just this slope through this point. So y equals 3/2 x minus 4 plus 12 in point slope form. And the normal equation is almost exactly the same, except I will use the opposite reciprocal slope to make it perpendicular. So negative 2/3 x minus 4 plus 12. One final example, just to make sure we're clear on how all of this stuff works. Given g of x equals 4x to the 7th, evaluate g prime of negative 1. So first, I'll find g prime of x. The constant multiple 4 comes down. The derivative of x to the 7th is 7x to the 6th, which means g prime of x is 28x to the 6th. And then I just do g prime of negative 1, which is going to be 28 times negative 1 to the 6th. Negative 1 to an even power is positive 1, times 28 is just 28. Alright, I hope that helped you guys out. Feel free to comment below if you have any questions.